So welcome back. We are here for our second seminar of today, for the formal part of today. So it's really my pleasure to introduce Professor Panagiotis Symeonidis, who I made a mistake and he corrected me before. Will speak to us about ChatGPT, but he told me he put just ChatGPT there mostly for interest people, but much more interesting it's LLMs and AI in medicine. So it's really my pleasure to leave him the stage, and I'm very curious to hear his talk.
Thank you very much, Emmanuel. First of all, I would like to thank you for hosting us here in the BrIAS Institute. I really enjoy my time here. My name is Panagiotis Symeonidis, and I come from Greece. The last 15-20 years, I work in data science and artificial intelligence. Okay, let's say 5-6 years before we started working with medical data. So what I'm going to present you is our research in the last 5-6 years in medical data. So here we can see the outline of my talk. ChatGPT and large language models in medicine. We will see also how we can use, how we use the deep reinforcement learning for medication recommendations, the graph-based methods for drug recommendations, and also we will see 3 demos in the area of medicine, like predicting the optimal dosing of a drug, telemedicine, and the Internet of Medical Things. So about these large language models, as you may know, in the last 5 years, it's like a thing that changed the way that we work, and this is an important change, like a game changer in our lives. So the main things, the main parts that are related with large language models are the tokens, which are the words. We have embeddings, so these are the vectors, and how we represent an entity. Also, the attention mechanism is very important. So it tries to identify what word is the most important in the sentence related to the target word. And also, the main thing that has changed in the way that we train our models is like that these models are self-trained. So it's not the idea that the scientist or a human expert give a class over or annotates a piece of information. In contrast, what is happening here is that the artificial entity is trained itself. So these are the main things, and of course ChatGPT is a generative pre-trained transformer. So there are 3 words here. Generative means that it generates content. So it can be an encoder or a decoder. So we will see them. It is pre-trained. So these models are trained offline. And that's why they require a lot of energy for their training. And also, the main element which runs behind this technology is the transformer technology. Okay, so let's see it in more detail. So we have the GPT, and as you can see here, the GPT-3 consists of 175 billion parameters. Okay, so this means that it's a neural network which consists of this number of links that connect the entities. And all these links, in the end, are trained by taking a weight. Okay, and this was like in 2020, and now it's like trillion parameters. So I guess there is a lot of scalability in this technology, and we have not seen the limits of this technology. So as we increase the number of the parameters, it seems that it is better trained. So the main idea behind these technologies is the word to back, like two algorithms, the skip grab, which tries to predict the context words given the target word, and the continuous back of words, which is the opposite functionality. So you try to predict the target word given the context words. So the heart of a transformer, and the ChatGPT is a transformer, it is a decoder, is the attention mechanism. The attention mechanism is the one which identifies which word is more impactful over the words for a sentence. So here we can see two sentences. I swam across the river to get to the other bank, and during this operation of the attention mechanism, the artificial entity is able to identify that the impact words for the word bank is the swam and river. So in this sense, it can identify that the bank is not about money and deposits, but it's about a river. So this is how it works in general. And here we can see the architecture, the blueprint of a transformer, which was initially introduced by Google in a paper. The paper Attention is All We Need. As you can see here, on the left, there is the encoder part. It's like it takes a sequence of words and decodes them in one word. So this is the functionality of a decoder. It takes a sequence of words and produces one representation of them. So it decodes them. And on the next on the right side of this figure, there is the decoder part, which is the opposite process. So it takes an embedding word and produces a sequence of words. So it generates content. So ChatGPT is a decoder, whereas other transformers like BERT, bidirectional encoder, is like an encoder. So here we can see the attention mechanism in operations of linear algebra. Like we have the query, the key, and the values. So as we do in databases, when we have a query, the information system tries to retrieve those keys that are related to the query and get their values, the same process is followed here. So when we take a sequence of words, we create 3 representations where in the Q representation, we have the target words, and for those target words, we want to find the keys which are relevant to the target words. So here we have matrix multiplication and other operations like softmax, and this attention mechanism is the heart of a transformer. So it is inside an encoder and a decoder. So this red rectangle is the multi-head self-attention mechanism, which means that we have multiple self-attention mechanism, like in a convolution neural network where we have images, and for every image we get different image maps to analyze it. In one we take the lines, in the second map we take the triangles, etc. In this case, when we have multi-head self-attention, in one parsing, maybe we analyze the connection between the words. In a second parsing, we may analyze the if it is presence or past, the type of words, etc. Of course, there are also residual connections followed by normalization steps. We have multi-layer perceptron here in the decoder level. So if we want to ask a machine to make a translation between from English to French, then we would need one encoder and one decoder. Okay, so this is an example here. So the encoder would take, for example, the words from English language and create it, would create some representations, some universal representation, embeddings of these sentences, and then the decoder would take them and would generate the content in the French language. Here we can see the overall architecture of a ChatGPT. As you can see, we start with some material like books, PDFs, Wikipedia. As we said, it is pre-trained, so we don't annotate anything. It just reads the first word, tries to predict the second word, and this is done frequentially, which means that then it uses the 2 first words, try to predict the third word, and so on. Of course, as you can see here, there is a fine-tuning process where there are some human experts which manually grading the responses of the ChatGPT in the final steps of this process. And of course, this is like a reinforcement learning process, which means that it rewards the good answers, the accurate answers, and it penalizes those which are not so accurate. And of course, this technology is very impactful in many areas, in many different aspects of our life, and we will discuss them for the domain of medicine, which can be considered as very impactful in small administrative tasks, okay, like to create some summaries. So if you have a long context of a patient with many lab tests and diagnosed diseases, which can be like hundred of pages, it can be applied to provide a summary of them. Okay, so for reasons of, let's say, administrative tasks, is very helpful. Of course, there are some things, some limitations in terms of the accuracy and also the transparency. So maybe you are not able to get a sufficient explanation about the clinical reasoning behind a decision, an automated decision. And also there are ethical concerns which should be considered for future. So we in the last years also we have the Internet of Medical Things, which means that there are smart wearable devices which can collect medical data and can be used for the precision medicine, the disease surveillance, prevention, and customized treatment plans. Okay, so the precision medicine means that we do not have diseases for all, the same disease for all patients. There are sub-diseases, okay? And these sub-diseases are defined based on the characteristic of each patient. So if the patient, for example, the DNA of the patient, the genomics of the patient, the environmental exposure of a patient, if he lives in a city with pollution or not, etc. So all these things are very important right now about the precision medicine. And of course, there are different wearables here. We can have a look like oximeter, glucometer, spirometer, ECG, electrocardiogram, graph, EEG, etc. So we can have many different devices right now, like smart rings. You may know about the smart ring of Samsung and many other accessories right now. So these LLMs initially have been used using the content like words, but right now they have started to train themselves with videos, images. So if you upload a X-ray in ChatGPT, it is able to analyze it. Also, video. There are already some papers that present the effectiveness of ChatGPT or MedGemini in terms of the clinical reasoning. And we will see some examples. So the main, as I told you, we work with data, and the last 5 years we used medical data. So we used the Mimic-3 dataset, which is a public available dataset. It is the data from a hospital in Boston, and there are like a lot of interesting information for those patients. Of course, the data are anonymized, and you can have, as you can see here, the information about the diseases that the patients are diagnosed, demographics, progress notes about the interventions and the procedures that are applied to patients. So here we can have also additional information like X-rays, CT scans, MRIs. We have also ECGs, a lot of information and a lot of different types of data. Here we can see an example of a woman which was, let's say, entered the ICU, the intensive care unit, and we can see that the reason was the fact that it was sweating, and the oral temperature was like 93.7, which means that it had, in Fahrenheit, she had some hypothermia. So this was like a reason why it is transferred to MICU. And all this information are, let's say, are words. And in our research, what we want right now is to make retrieval of mentions. Okay, so in a long record of a patient, we want to identify specific characteristics. Let's say here we see an example which says, okay, try to find those quotes which are referring to hypothermia. This is like an example comes from the MedGemini paper of Google. And as you can see in this Mimic-3 dataset, it identifies the fact that a quote that has to do with that sweating, oral temperature 93.7, and constitutional hypothermia. So this is one task that we can ask from, with a prompt from a large language model. And also, we can make even more tasks, like to ask from the LLM to give us a clinical reasoning. What was the reason behind a diagnosed disease, for example, or a symptom? And here we see that there is a conclusion. Yes, the patient has a history of hypothermia. The combination of a low temperature reading and explicit mention of hypothermia in the patient's record provides a clear confirmation. So this technology can also be used in order to provide clinical reasoning. Okay. They have evaluated this MedGemini effectiveness over other baseline methods. As you can see here, the task was like electronic health records, needle in a haystack. So it means like I try to find something in a lot of information. As you can see here, it's very comparable to other methods, to the baseline method, which had already used an annotation process. So it was like the information was annotated by experts. So it's really comparable to this, and there is, you can find it in the technical report of Google about MedGemini. It's like 60 pages. So for our research team, what we are trying right now is to extract medical mentions from the Mimic-3 electronic health records. So we have this data, and for example, for this patient, 109, the fact that it sweats, all the progress notes, the oral temperature, and all other things that were written from the doctors. And what we were trying to do is to predict the diagnosed diseases. Okay, so these are the diagnosed diseases for this patient. And this is a task that right now are trying to do. So the first task is entity recognition task to identify the influential words. And the other is the entity linking task to associate one word with a specific diagnosed disease. Okay. So in this, I could show you, for example, here, some code, like how we have the data. So if you see here, we have, these are the data that come from the Mimic3 dataset. So we have a Python code where here is the patient 109, and for this patient we can have different measurements, vital signs, like the heart rate, the diastolic and systolic pressure, the respiratory rate, and as you can see here, there is information about what happened after exiting the ICU, after the ICU discharge, and the diagnosed diseases like acute kidney failure, and the procedures that are applied to the to this patient, like the interventions of the medical doctors, as you can see here, hemodialysis. Also, we have the prescriptions that are applied and the drugs which are given. Here we have the NDC codes, the drug name, and the dose, and we know the exact time that it was delivered, so 4.4 hours after the ICU entry. So all this information is available for us, and of course, the input events, laboratory tests, and we have some interesting diagrams about the heart rate, how this patient is, these vital signs of the patient can be compared with the overall population characteristics, and the systolic and diastolic pressure, and all this information can be used in order to infer some interventions, or for our task in particular, what we wanted to identify was like to predict the drug combination that were given to the patient after they entering the ICU, the first day in the ICU, that he entered the ICU unit. And of course, there are other information which can be used, like the ECG, electrocardiograms, graphs, and also the chest X-rays, which are available in the Mimic3 dataset. So, about the artificial intelligence algorithms that we used. These are two papers that we have published in 2022 about reinforcement learning and deep reinforcement learning. So the questions that we wanted to answer here is, can we minimize the unwanted side effects among the drugs of a recommended treatment to have less toxicity for the patient by giving them substitute drugs with less implications and impacts? So this was the main question that we wanted to answer. And what we trained here, it was like an artificial agent. And here you can see in this framework of reinforcement learning, we have states, we have some actions. We have also some functions that are applied. So the artificial agent performs some actions, like predicting the drug combination, or predicting the dose of a drug, like how many units of insulin a diabetic patient should take to regularize its blood, its glucose in blood, its glucose level in his blood. And so after the action that it performs, it gets a reward. So the reward is high if you predict the ground truth action, the action that the medical doctors had taken. Otherwise, it penalizes this choice. Okay, so this is the loop that it is followed. So the agent takes some actions, and then these actions are evaluated, and we give them a reward or a penalty. And we have three functions, as you can see here, the transition probability. So what is the probability of moving from one state, a clinical state, to another clinical state? So the clinical state may be, for example, the blood glucose level of a patient from one level to another, the reward function, and the policy. The policy function is important because it decides the strategy that will be followed. Okay, so in this framework, the strategy is important. For example, am I going to exploit the best solution that I have already found, or should I explore a bit more and maybe choose randomly another action which in the overall process would give me more benefit? Okay, so this is like the policy which should be followed by the algorithm. And of course, there is a lot of arrangements. In this work, we have some other papers to compare with, and these papers were like GameNet. There were really deep neural networks, like they were using the drug-drug unwanted interactions. So those interactions that are harmful for the patient. They are using also the electronic health records of the patients, and deep neural nets like convolution neural net, relation graph, and deep Q-learning algorithm. Okay, so these are like methods which we compare our own method. And of course, what we wanted was like to optimize our effectiveness by also reducing the unwanted drug side effects. So if we are able to find substitutes which could who could heal or recover the disease, but with less toxicity. Of course, this is a work which should be performed along with the medical doctors. So we are scientists in computer science, and we can make quantitative analysis of these results. We can measure the precision, the recall, and the effectiveness of the model, but of course we need also the qualitative evaluation, and this of course can be given only by medical doctors. Here we see the main function of the Bellman equation, which is used in Q-learning. Okay, here we see the Q-learning algorithm, and of course the deep Q-learning, the deep Q network is the implementation of Q-learning using neural nets. Okay, so it's an old algorithm which is implemented by using neural nets, technologies like TensorFlow, PyTorch, etc. And as we can see here, there is the when the artificial agent selects an action, it is given a reward based on the benefit that it gets, and also it has another second reward based on the future benefit that it would get. So we have two rewards here, the instant reward and the future reward. Okay, as this is these two terms of this function. equation. And here we can see it in the Q-learning algorithm in a pseudocode. And we have the states, the actions, we have the reward function, the transition probability, and the discounting factor, which means that this gamma parameter, this means that as we try to reward future states, we have to discount their weight, okay? Because it's future. You cannot go you cannot predict very far from the presence. So, of course, we have the reward function here. As you can see here, if we predict the drug that it is prescribed to the patient from the real medical doctors, then we reward the algorithm. Otherwise, we penalize it. And of course, also, we take under consideration the drug-drug unwanted interactions, which means that if a drug appears in many harmful drug-drug interactions in the drug-drug interaction graph, then this is something that reduces its, let's say, weight. Okay, so these are the two things that we have in our reward function. And we use the double deep Q-learning algorithm and compare it with other algorithms for the mimic-3 subset and the cancer dataset. There are two datasets here. As you can see here, we have the drug-drug unwanted side effects. In one dataset, the side effects were unwanted, whereas in the cancer dataset, the drug-drug, we were using synergistic effectiveness, like in chemotherapy, where you use two drugs to make a faster recovery of the disease. So here we see a slide from the mimic-3 dataset, and it's about 40,000 adult patients here, and I have already discussed about this. The precision recall was the measures that the metrics that we used in our experiments, and also here we have an evaluation metric for the drug-drug interaction rate, which in the numerator counts how many are the pairwise unwanted interactions to the total number of possible unwanted drug-drug interactions based on the provided drugs. Okay. As you can see here, there are drugs with many unwanted side effects. And so this was like an evaluation metric. Here we can see an example of how our algorithm, the DQN, provided drug combinations based on the diagnosed diseases of a patient. Okay, here we can see this patient is diagnosed with ischemic heart disease, pulmonary embolism, and the DQN predicts successfully for cardiovascular disease 2 drugs, but fails to predict any medication for hypothyroidism and depression. So this is like how we perform and how we evaluate our predictions based on the ground truth. And of course, here we can see that by using the patient's drug information along with the drug-drug interaction, we can really reduce the number of drug-drug unwanted interactions. These are like quantitative results, and as far as the qualitative experiments, we asked 5 medical doctors to rate the predicted drug combinations. So they had to answer 2 questions. The first question is how well diseases are covered. How well diseases are covered based on the predicted drug combinations. And the other question is how severe were the unwanted drug-drug interactions. And here you can see that when we run the DDQN only using the electronic health records, this bar is really high. So we have severe unwanted drug-drug interactions, whereas when we take under consideration the EHR along with the internet database about the drug-drug unwanted interactions, we really eliminate these severe unwanted drug-drug interactions. Okay, so this was really good for our research. Another research direction that we had was about graph algorithms. Okay, so here is like 3 papers that we published for graph-based methods. And the question here is how can we extract frequent patterns to infer relevance among the participating entities in a knowledge graph. Okay, so in a knowledge graph we have many participating entities and we have many relationships, many different types of connections between the entities. Okay, so here we can see a medical graph that consists of the patient, the disease entity, the interventions, and the drug information. Okay, so we can use this graph in order to identify similarity, to perform similarity search or relevance in graphs. Like we can use graph-based algorithms like SimRank or random walk with restart in order to identify similarities between diseases. Okay. And in this case, what we exploited was like the metapath, which is a sequence of relations between different node types. For example, in this graph on the right, we have 3 types of entities. We have the patients, we have the treatments, and in each treatment we have different tracks. So this is like a graph, multidimensional graph with many entities. And on this, we want to identify those metapaths which are very frequent. Okay, so in this formula here, we can see that we can compute the similarity between 2 objects based on how many are the instances of a given metapath. In the numerator, we have the number of instances that connect the 2 entities, whereas in the denominator we have the number of instances of a metapath which start from one entity and return to itself. Okay, so in this case the intuition behind it is that 2 similar peer objects should not only be strongly connected but also should have in the graph should have similar visibility and reachability, let's say. And of course, in this case, when we identify these frequent metapaths, we can use them in order to justify a recommended drug combination. Okay, as you can see here, if we want to recommend a drug to a patient, we can use these metapaths, the instances, and that we identify in the graph, count them, and use them in our as an explanation for those predicted drug combinations. Okay, so a different metapath, like here the drug patient drug or the drug treatment drug, can be used for enhancing the predicted drug combination and justifying it. And in this case, the important thing was, again, to minimize the harmful drug-drug interactions, which can be seen here in this diagram. But of course, another important thing that we count was the explainability coverage. So how much were you able to explain a recommended drug combination? Okay, so this is what we try to count, and this was like, we use this formula here, which counts how many are the instances of a metapath that can be used to justify a recommended drug combination. Okay, so in this work, we work with knowledge graphs, and the PathSim algorithm was able to infer these drug recommendations. And now I can continue with some demos of our research. I already show you the Python notebook Jupyter, which is used for the Mimic3 dataset. So here we can see some slides. It is related to another patient, of course, here, but we can see the diseases that the patient has. Also, some graphs which show the glucose levels in his blood. As we can see here, he is in the ICU for 24 hours, and we can see the levels of the glucose in his blood, how they evolve in comparison with the other patients' population. So it could be used as an alerting mechanism for the medical doctors, of course. Another thing that we performed was like the predicting the dose of insulin for diabetic patients. This is an ongoing research right now. So we knew the amounts of units of insulin that diabetic patients takes, and we wanted to predict it. So in this case, we have created a web app for diabetic patients. So this is the second demo. As you can see here, what we want to identify is what is the optimal dosing of insulin so that a diabetic patient does not have high or low glucose in his blood. And this can be formulated as a two-dimensional matrix. We have the rows are the patients, whereas the columns are the different units of insulin that we give to those patients. And inside the cells, we can store the glucose levels in the blood of the patient, which result after the application of the insulin. Okay, so this is how it is defined. As you can see here, when the glucose level is in the accepted range, for example, between 80 milligram of per deciliter to 120 milligram per deciliter, then it is like the true, the terminal state in the reinforcement learning algorithm. Okay, so this is the terminal state. And of course, the idea here is that to increase the time in range of the patient. So in this case, what we want is, can we predict those insulin units which would make the patient to remain all the time in this green zone. So the green zone in this diagram, in this chart, is the zone which is the amount of glucose levels that we consider as regularized, and this is what we try to optimize. So here we see the actual and the predicted glucose levels. Okay. And of course, we have also the task of predicting the dose of insulin for the patients. Of course, this is like a time series process. You use all the information in order to predict the next choice. And as you can see here, the random forest was the one who has the best results in terms of mean absolute error. Over the 5,659 patients, we have also the standard deviation, the confidence interval, and the root mean squared error. The worst error of mean absolute error was like from linear regression, but of course there were other machine learning models like the random forest who had the best error, the lowest error. The same for the insulin dose prediction task. The mean absolute error here is 1.85, and the random forest is the one that has the lowest error. Again, based on this algorithmic framework, which was implemented in Python, we have created a web app, and we see here the name of the web app is ChatGluco, chatgluco.com, and it has the Flask API with the algorithms like linear regression, random forest, XGBoost, and also we have implemented with Laravel framework, and we have also the database here. And yeah, I could show you some, yeah, I could even go to the website. Okay, I need to log in again. Okay, so here, what we try is to do for a patient is to keep track of the diary of interactions and the measurements. And as you can see here, we have like the glucose levels in blood of the patient before meal. We have the food carbohydrates that he's going to have during the lunch, and the insulin dose that we predict, and the glucose after meal, the glucose level after meal. So this is the diary here, and of course we can have a new record. For example, let's say 180 glucose levels in blood. We can choose something that we can have, let's say one banana here, the quantity. So we can have the carbohydrates, and also we can calculate the insulin dose. Here we will use the sliding scale protocol. So we have a computation of the insulin dose that it is needed based on the food carbo and the glucose level in his blood. And this can be, let's say, accepted or not from by the patients or the guidelines. So this is like the diary, how it works. And in the end, is the diagram that we can have. For example, for this patient, we can have a diagram, a chart that shows us the glucose level over time. So as you can see here from this diagram, a medical doctor can have very fast identification of the number of times that the patient is beyond the range that it should be. It is like 59% of the measurements. It is above the ranges that are in the green zone. Okay, so also we have the hypoglycemia here cases, and we believe that if you keep track of this information, a patient, over time, we will manage to make these measurements better over time, because he will also see this and try to improve the choices that are made. Of course, in this chat gluco, it is chat because we believe that we can also make it able to act as a chatbot for the patient, which means the patient could give, for example, a constraint in this artificial entity, let's say, and say, for example, give me a meal that has 50 carbohydrates, okay? And so the artificial agent can deliver a meal which is healthy for the choices of the patient. This could be an idea of extending this framework. Okay, let me go back to the slides. So here we can see some user interface of this chat gluco. We can keep some basic information about the medical details of a patient, like the diagnosis, if it is type 1 or type 2, the weight, some measurements about the glycated hemoglobin. Here we have seen this diary, the chart. The time in range is very important for the medical doctors. This is what they want to optimize. So if you can be able to have the time in range of a patient above 85%, it is like very, very good goal for a medical doctor to achieve this. And of course here we can see how we can identify the line which represents the insulin and glucose levels interactions. Okay, the correlation between glucose and insulin values. So now I will finish this talk with the third and last demo, which is a simulation. And this is for a heart failure, let's say, alert. In this case, we have a simulator. In order to simulate a smartwatch, we use a web-based app to produce vital signs. Okay, this is the IoT sim web.app simulator. So we can extract vital signs for patients like ECGs, electrocardiographs, blood pressure, heart rate, blood oxygen, temperatures. And what the task here is to try to monitor the patient and alert in case that some vital signs are over the acceptable ranges. Here we see a slide that shows the ECG, which shows the electrical activity in volts of the patient's heart over a period of time. And so we want to identify if there are, let's say, problems with inside this electrocardiogram. Few words for the electrocardiogram. The main idea is like a signal, an electrical signal that consists of measurements of millivolts. And what we measure here is the PQRST signal. The PQRST signal is like a signal of peaks and valleys, and it represents how well is the depolarization of the atria, the depolarization of ventricles, and the repolarization of the ventricles. So it's like the three signals, the P, the QRS, and the T wave. And based on this signal, we can identify, for example, the heart failure, the ischemia, which happens when we have a narrowing of a large coronary artery. Okay, in this case, it causes a decrease in blood flow. And as you can see here, the normal case is when this T is like a small peak, whereas the problem is when this T wave is negative instead of a positive signal. Okay, so here we have a trough, and this is like an identification of the problem of ischemic heart failure. So in this case, we can have like a blueprint. We have created a blueprint in Node-RED in order to make some alerts that we have based on the electrocardiogram, the PQRST signal, the PQRST waves, the heart rate, the blood pressure, the oxygen in blood, and the temperature of the patient. And all these values could raise an alert for the medical doctors. And here we can see the server-side dashboard, which gives us, in this simulator, the overall characteristics of a patient. We can see here the amplitude and longitude of the patient in this map, and also the blood pressure, the electrocardiogram, the heart rate, oxygen, and temperature. So in this case, you can have a monitoring of the patient clinical status in a distance. Okay, so it's like telemedicine, let's say. And yeah, of course, there are also other possible research directions. Here we can make recommendations for the physical activity of patients using a smartwatch or biosensors. Also, recommendations about healthy food choices, which is something that we are interested in performing. And finally, what would be a good idea for us is like to incorporate patients in our prediction models, other information like the environmental exposure and bioindexes like sun, humidity, pollution in our models. Last but not least, I would present the idea also, which is beyond medicine. As soon as here I know that there is also a research direction in environmental research. So what we are also doing the last, let's say, 6 months is like we collaborate with the industrial, with the company, which is its task is to predict the larvae population in breeding sites or adult mosquitoes in order to spray them in advance. So this is also something that we are interested, and of course we implement algorithms, and these algorithms can be applied in different data, okay? Because we have health data, but also the data could be from other domains. It could be, okay? So in this case, I guess you should try to spray in advance and predict the burst in terms of larvae populations or adult mosquitoes based on some variables like the dryness of the breeding site, the date, the temperature, and of course some other environmental parameters which I'm not so familiar with. Okay, so this is my talk. Thank you very much for your patience, and I will be glad to answer if there is any question.
I imagine there will be multiple questions, so Luca.
Thank you for the presentation. For the RL case that you have presented, the reinforcement learning case, you have explained how the reward function was, but what about the transition probability distributions? Because this agent will try to do things that normally you cannot test on people. How do you...
In this case, in the transition probability function, we want to identify the cases where from one state you move to another state. So, for example, in this two-dimensional matrix, we have the patients, and we make we take an action. So we take some specific number of units in terms of insulin, and then we have a new state. So here we can compute all the transition states from one state to another state. You can have all the transition probabilities. So this is our input data for us. Of course, the reinforcement learning algorithm in general has the problem of not being able to apply it and take this decision online, but we perform this offline. So we have all the data from previous actions of the medical doctors, and we use them, we reproduce them in order to make the artificial agent to perform action based on the historic data. Okay, so this is the idea. Okay.
Other questions?
Hey, how far are these projects from talking to notified bodies or FDA and make them into a validated product?
How far are these projects from being able to let's say, use them for real-life cases, you mean, eh?
Yes.
Okay, so right now these are prototypes. What I have shown to you are prototypes. What we try to do is to collaborate with medical doctors, for example, with medical doctors that are in the specialty of diabetes, and use this software in their clinic so that we have real data, because this data come from the medical, the MIMIC3 dataset. Okay, so we would like to have real data from patients. Of course, this framework can be used with patients, diabetic patients, the one that I have, the chat gluco, in order to monitor this, their measurements, not for predicting them if we would use them for real cases. Okay, so it's like a prototype, it's not for...
There was one.
Thanks for an amazing presentation. I want to understand, perhaps it's not related to your work, more is related to the data set. Since you are implementing a rewarding policy based on the advice, diagnosis of the doctors, how can you manage the uncertainty of that data? Meaning, for a trained eye, doing the diagnosis of a fever can be fast, but for a newly graduated doctor can be challenging. So you don't know the quality of the diagnosis and if they were fake positive before the final diagnosis. So how can you handle that within the model? Knowing, because in database models, we know that garbage in, garbage out, meaning if we don't filter the data, we cannot create a model that is reliable enough. So how can you manage that variation of the profiles of the doctors and the training levels of the doctors?
I don't understand. What is the word?
I mean, when you are diagnosing, when you are getting the diagnosis from a doctor, I imagine that it's not the same doctor that is giving the diagnosis to all the patients of the data set.
Yeah, and you are
So
not
you have
sure
a
if this
variation.
is, you mean when we use as a ground truth the decision of a doctor, this could result in not a good
In a fake positive.
result, and so why we use them as a ground truth? This is the question. Huh?
Yeah, actually, you
okay,
you can have several diagnoses. I assume that in the data set you have the last one.
Yeah.
But how can you base
in-
a rewarding policy based on that
Yeah,
different levels of
understand your
training?
question. Yeah. Nice question. Well, the idea here is that in this research, there is like plenty of papers that we follow the same procedure. And as I told you, as a patient enters the hospital, we keep track of the patient during the days that he's in the hospital, and then as soon as he goes to the ICU, we stop our model in the training process, and we want to predict what are the drugs that were given from the doctors to the patient in the first day of his entrance in the ICU. Okay, so this is the process. Of course, here there are different things which could be not effectively measured. For example, as you said, maybe the choices of the doctors were not the good ones. That's why we had this qualitative, let's say, evaluation, where we give specific prediction of drug combination, and then we asked medical doctors to see the medication predictions, and then see how well these medications cover the diagnosed diseases of the patient, and if there were, let's say, unwanted drug-drug interactions, if they were severe or not. So this was also something that we had studied. So this was like the idea. Another problem that we had is that we did not, we were not able to give drug combinations for all the diagnosed diseases. Also, if you have seen, there was like one result which was with really small recall, like 4 or 10, which means that we were not able to provide, let's say, the ground truth drug combinations for all the diagnosed diseases. So this was also another thing. Yeah, I think I covered your question.
Was a question there?
My question was actually much more basic than the ones you already got. So, because you lost me at the moment in your talk between the first part, which was all about LLMs, and then you moved to the Q-learning example. And I know that deep reinforcement learning is also applied to LLMs, but I wasn't quite sure what the connection in your work is between the LLM technology and the reinforcement learning.
No, this was like two different research directions. The first was like the reinforcement learning that it is performed in LLMs as a last stage of the refinement of a ChatGPT, for example, large language model. The other is like algorithms that we used, like algorithms from DeepMind, which is like a company from Google. DeepMind, the DQN or the A2C algorithm that we used in order to make predictions. Of course, in deep learning, these algorithms are very effective right now. So the state of the art in algorithms right now is like deep reinforcement learning. So it's very, very effective. and they are used from many right now algorithms, and the heart of the MedGemini LLM is a reinforcement learning algorithm. Okay,
Right.
so these algorithms are
Right,
very, very effective.
All right, but then so in the results, in the demos that you presented, there the LLMs don't play a role. Also not in the demo that you called that started with the word chat. So there was
Yeah, the
again-
chat is like we want to make it a chatbot. So yeah, so the patient could deliver could provide some prompts to the patient to the let's say to the chatbot, and get a more let's say it's not just a retrieval,
so
but
more interactive interactive experience.
a more intelligent answer.
Right.
Because if a patient goes to this chatbot and say, okay, I want to I need to get 50 carbohydrates because otherwise my glucose level in my blood will become high. So then this, let's say, intelligent agent could provide different diet dishes, which would be helpful for healthy for the patient. And yeah, I think that it would have a good, let's say, impact for the patients. Yeah.
So, there is a last question. Yes, there is time for a last question. After you have spent all the time behind the console, we cannot say you know.
Thank you very much for the nice presentation. I have two questions. So the first one is about the diabetes data. Is it open source and available? And the second one is about the RL perspective. So what was the features of the patient that you included in the state space? Because that's also something that highly, influence the level of the dosage of the insulin on the specific patient. So what was the features that you embedded for the states?
The states?
Yeah.
Yeah, okay, yeah, sure. So the code, if it is open sourced,
Yeah.
Our code or the code of
The data set that you should.
The data set is definitely available. So the MIMIC data set is available under the FISIONet framework. Okay, it is also from MIT. So to get access to this data set, you need to undergo a small seminar, let's say, and after this they will grant access to you.
Mm-hmm.
So this is the first thing. As far as the data, the second question, you wanted to give you an insight about the states.
Yeah, for instance, the table that you actually showed.
The states there. In this case, we have, let's say, here.
Yeah.
Here the states are different units of insulin that the patient gets.
Okay. So for individual patient, you don't have any.
These are the actions. So the actions is the different insulin units that the patient gets. Okay, this is the action that the artificial agent takes. Okay, if I give 5 units of insulin, what will be the result? If I give 15 units of insulin, what will be the result? And if I give 10 units for patient 2, you see it gets a 100 glucose level, which is the terminal state, which means that we consider this as a state that we don't do anything, so we just wait there. So this is how we formulate the problem in this in predicting the optimal dose of a drug. But in case of, for example, of drug combinations, the states are the states are the
because, for instance, 5 units of insulin actually affects differently on a patient who has actually 15 years old and other patient who has
this is true. This is just this is true. Yeah, you are correct. This is like a toy example here. We see a toy example. If we see the real data, of course, here you need also the timestamp, because you don't know here if it is the past, the future. So you need also the timestamp and all the other characteristics of the patients. Yeah, but this is like the heart of the problem is this. And then, of course, we need additional data to express the real situation. Yeah.
Thank you.
Okay.
Okay, so with this, I propose to thank again the speaker.
Thank you very much.
And we can close here the formal part of our meeting. So you are all invited to stay for a coffee, for discussions with the fellows, with the researcher present, and so on. We are more than happy to stay longer and discuss. And for the rest, see you next time on Thursday.